A macrocycle can be described as a sequence of mathematical transformations that compress a state, move its probability information through a transition rule, dissipate reverse energy, and return its phase to a starting class. The main goal is to see which parts of the construction are rigorous assumptions, which parts are geometric motivation, and how the cycle stays consistent from its initial state to its final reset. The explanation begins with the compressed state, because every later stage depends on having a well-defined normalized input. The state starts in a Hilbert space, which is a vector space with a length rule and an angle rule, so a state can be treated like a vector whose total probability size is 1. The compression stage applies 4 orthogonal projection operators and 1 unitary phase operator, where a projection can only keep or reduce length while a unitary operator preserves length. The combined compression operator is the product of the fourth projection, the third projection, the phase operator, the second projection, and the first projection, so the whole product cannot increase the length of any state. If this product sends the initial state to the zero vector, normalization would be impossible, so the construction must assume that the compressed vector is not zero. When the compressed vector is not zero, the normalized compressed state is formed by dividing the compressed vector by its own length, which makes the new state have length 1 again. The frame 5 phase lock expression gives a geometric reason for using a symmetric 120-degree structure, but it does not by itself prove contraction in the later probability dynamics. The rigorous contraction claim belongs to the pump phase, where the compressed state is converted into a probability vector by taking the squared sizes of its coordinates in a chosen basis. A Markov transition kernel is a matrix of non-negative transition weights whose rows add to 1 in the row stochastic convention, so it sends probability distributions to probability distributions. During the pump interval, the matrix can depend continuously on time, meaning the transition rule changes smoothly while still remaining a valid stochastic matrix at each instant. For strict contraction, the theorem must assume a number lambda between 0 and 1 such that the distance between any two evolved probability vectors is at most lambda times their original distance. This contraction assumption is important because stochasticity alone preserves valid probabilities, but it does not always force different probability states to move closer together. The quaternion centroid is defined by applying each rotational operator and its inverse to the initial state, adding those results, and normalizing the sum when the sum is not zero. If the rotational operators are unitary, each inverse is the same as the adjoint operator, so the centroid is built from norm-preserving rotations before the final normalization step. The active current is then interpreted as a time-dependent flow aimed toward this normalized centroid, which gives the pump phase a target direction in state space. The collapse phase introduces a torus parameterization, where two circular parameters track the changing position of the collapse inside a two-dimensional periodic space. The resistance functions are continuous and non-negative, so they can vary smoothly along the torus while never contributing negative resistance. A reverse energy functional is a non-negative quantity that measures the amount of reverse energy remaining in the system during the collapse. The collapse is dissipative when the rate of change of reverse energy equals a negative sum of resistance weights times squared mode strengths, because every term in that sum is non-negative. This means the reverse energy cannot increase, and it strictly decreases whenever at least one active resistance mode has a positive weighted square. The statement that the longitudinal field remains protected is an extra condition, so the proof must separately impose conservation or a lower bound for that field. The final phase uses modular arithmetic, where two phase angles are considered the same if they differ by a whole multiple of 2 pi. At each step, the phase is updated by adding a phase increment, so after the whole cycle, the final phase equals the initial phase plus the sum of all increments. Encapsulation requires that this total phase increment be congruent to 0 modulo 2 pi, which means the accumulated rotation leaves the phase in the same modular class where it began. With the non-Zor normalization assumptions, the explicit contraction assumption for the Markov kernel, the dissipative energy inequality, and the modular reset condition, the macrocycle is mathematically structured as a consistent step in a larger proof.